right, we're going to talk a little bit more about forces and radiuses that are perpendicular to each other. This is Rod. Hi, Rod. Rod brought a friend, Bob. Hi, Bob. You guys know that gravity is what makes Bob go back and forth. You also know that gravity listens to my favorite band, One Direction. It only pulls Bob straight down. So when Bob is over here, he's not moving in the direction that gravity is accelerating him. Gravity is accelerating him straight down, isn't it? Something by yay. The way I can figure out the direction that he will go is always perpendicular, always tangent to the radius, is I will take that gravity arrow and I will break it into a component that is parallel to the radius. So hopefully this arrow is parallel to the radius. It ain't bad. Something about yay. And this red arrow then goes tail to tip to the parallel one to become perpendicular. This arrow right here, that arrow is the perpendicular component of gravity. That perpendicular component is the torque. This is the direction that Bob will move when I let go of Bob. So that is always going to be perpendicular to the radius. And a force that is perpendicular to a radius ought to sound familiar. That's what a torque is. So this force then is very, very long when we're at maximus displacement. As Bob goes this way, that torque or that force ends up dropping to zero at that location. Then Bob keeps going, doesn't he? That arrow magically flips because it is a gravity component. It is always pointing towards the lowest spot of Bob. So it will point here and it will get smaller and smaller and smaller and disappear and then go in the opposite direction and get longer and longer. So as Bob goes back and forth, what I want you to envision is this red arrow always perpendicular to the radius and getting longer and then shorter and then longer and shorter and longer and always pointing towards the center. This is the torque arrow. Alright, the red one perpendicular to the radius, and that was a decent prelude to simple harmonic motion, which we will get to in a little bit, but please remember how that red arrow changes. It will help you a lot when we get to simple harmonic motion. And another example I'm going to share with you is my record player. Again, right here. You remember this guy? This is just a plain old record player. I put an arrow to represent a radius, so a radial vector pointing outward. It is not a force vector. It is a radius distance vector. Alright? So if I put a nickel on this record player, and if the record player were frictionless now, you guys know that record player would spin right underneath the nickel. The nickel wouldn't move if the record player were frictionless. It is not frictionless, so when I put that that nickel right there, it goes in a cycle. So there must be some force pushing it in a direction that is perpendicular to that radius, because the direction that that nickel is moving is perpendicular to the radius, isn't it? So it's moving in that direction. Again, that's the torque arrow. I used the red one last time, so I'll use the red one this time. It's always perpendicular to the radius. That's what's supplying a torque. That should sound familiar. A radius times a force that's perpendicular to each of R. Alright? Now, what I want you to realize is that torque that friction is pushing this nickel the whole time is causing that nickel to accelerate linearly. That would be a tangential acceleration. It's also causing it to change its rotational velocity. From right now, it's going in circles at 0 radians per second. As soon as I push it now, he's going at a different number of radians per second. So if your radians per second number changes, you have alpha'd. Haven't you? Because you guys all know that alpha is the rotational A. So, torque is what I am specifically referring to in this case. Torque, you know, is a radius times a force. Those two are vectors. They will be perpendicular to each other, so you will push the sign of theta if they aren't, and that will give it a direction. What I'm going to draw is that turntable. That could be the nickel. Its force is perpendicular to its radius. So there's an R, there's an F. Okay? I'm going to talk a little bit about that force right there. Okay? You guys all know that any given force is equal to right? In MA, a force is equal to mass times acceleration. Someone should make a law, okay? If I'm going to take a force, I'm going to multiply a radius. If I'm going to calculate a torque, I'm going to multiply a radius by one of those forces. So I could replace that F with an MA, couldn't I? And so when I calculate torque, what I could do is say it's a radius, that R, times that force, which is going to be an MA. All right, the radius is a direction, the acceleration is a direction, there's a torque. Okay, I'm not going to write sine theta because it's already 90A. Now, here's what I want you to realize. That A is a tangential acceleration or a linear acceleration. The direction that that arrow was pointing is tangent to the circle. There's the arrow right there. Do you guys remember how linear and rotational quantities are related, don't you? Like if this nickel were to rotate from here to there, and I would ask you, what's that linear distance between those two locations? What's that arc length? You would say it's the radius times the angle. So this is just review here. Remember, a distance, or sometimes an S, is called an R times a theta. Some students earlier this year called it thetar. But what I'm showing you is how linear is related to rotational. They are related. A linear velocity is a rho omega. That should sound familiar, right? V equals rho omega. A tangential velocity, the speed at which this thing's moving linearly, is related to how fast it's going in circles and how far away it is from the centaur. Now that A is the one I'm referencing today. That is equal to alpha. Alpha, again, is the rate at which your omega changes. So if I have that A right there, do you literally see a swappertunity? Hey, I think so. So what I'm going to do is I'm going to say that torque is now the same thing as this R times that M. That A I will replace with an R alpha. That all together I'm going to simplify to call an mr squared alpha. That's what torque ends up being. Now this mr squared, that's the mass of whatever's going in circles. It could be the mass of that nickel. It could be the mass of Bob going back and forth. It could be the mass of anything going in circles. This R is however big the circle is. So this quantity right there is a constant, isn't it? It's whatever it is. And it has a very special quantity. It's so special that I will call it a specific quantity, and the letter I will choose to refer to it as is I. So torque is equal to I alpha. So I is mr squared. Now I refers to an object's resistance to rotating. It's called the moment of inertia. It's a quantity of inertia, which is why it's called an I, but it's not a linear resistance, okay? It's a rotational resistance. When things rotate, they have a resistance to rotation, right? Bob has a mass of whatever it is, and that mass is located a certain distance from the axis of rotation. That's his R. And that's whatever rate he's going in circles. Is it easy or not easy to go in circles? I don't know, but what you can tell is if I shrink the R, he goes back and forth much more frequently, doesn't he? So it seems to be easier to go in circles that way because his mass stayed the same, but his R is different. So mr squared put together gives you the I. Now that's also why I have these 2 meter sticks again. I've been using these sticks quite a bit. This is just a stick with 2 C-clamps way out at the end. This sucker is more difficult to rotate than that same meter stick with 2 C-clamps right towards the middle. The mass is close to the center of rotation, therefore it's easier to rotate. I mean, look what I'm trying to do, or look what I'm doing with the 50. I'm balancing it, I'm wiggling my finger just a little. And look at the effect it has on the meter stick. That thing's dancing like crazy. If I do the same thing with this, once I get her balanced here and I move my finger back and forth, it's doing very little, if not nothing, to the rate at which this thing's going in circles. So this is much more stable than this one, all right? This has its mass way far away from the axis of rotation. This one has its mass close to the axis of rotation, so it's easier to rotate, smaller I. Another example of I, since we are not in the middle of baseball season, is baseball. You guys all know you do one of these, right? Your little league coach will tell you, well, gosh, if you can't move the bat fast enough, if it's too difficult to get to rotate, all you do is just move your fingers there, put your hands up there, right? You choke up a little bit. Now all of a sudden it's easier to get this thing to rotate. That's because the mass becomes closer to the axis of rotation. You have lowered the I, so it's easier to get the sucker to go in circles. That's all I want you to visualize, is how close the mass is to the axis of rotation. And the same object can have a very different I depending upon its axis. This guy is difficult to get to go in circles over here, but if I hold him by the center, it's easy to go in circles. And that behaves very differently than if I were to twirl this thing like this. This is easy to go in circles. So what the axis is and where the axis is changes an object's I, okay? The mass stays the same, but its resistance to rotation does not stay the same. So these same 2 meter sticks, if I were to throw them at you like a javelin, they would behave the same because they have the same mass. They'll move linearly identically. They would behave the same moving linearly. But rotationally, they're very different. Boy, you can even tell. They're very different rotationally, okay? Plus, a meter stick around its end is more difficult to rotate than a meter stick around its axis here. All right, I'm going to take another bit of a road trip here, okay? We're going to go back to my living room, and the fire is not going, sorry, but what I want to show you is this. I put together a little ramp with a calculus book, because boy, I could really use some tutorials, all right? But what that ramp is here to show you is how different things respond differently to rotating. This is a solid disc. It's just like a really big hockey puck, all right? It's just a solid disc. This is a same mass, but it's a hollow disc, all right? So what I'm just showing you is this is an inclined plane. You can tell that sucker's rolling, can't you? This guy should remind you of a meter stick that has the 2 C-clamps way out on the edges. So as it rolls, the axis of rotation is smack in the middle. So all of the mass is very far from the axis, from the centaur. This is a solid disc, right? That's the axis of rotation right there as it rolls. The mass is distributed more evenly, so it has the effect of making this mass closer to the axis of rotation. So this has a smaller I, this has a bigger I, which means this one resists rotating more. This one resists rotating less. So this solid disc will be easier to rotate than this hollow disc, even though they're the same mass. And what I will show you is these 2 items just rolling down the ramp here, trying to let them go at the same time. And you see that solid disc go, ooh, see? It rolled down the bottom first. And, if you can't tell, the black one, that solid one, stopped a lot sooner than the hollow one, because if it's easier to start, it is also easier to stop. It has a smaller I. This is some good old-fashioned tomato paste, huh? This is a hollow can of tomato paste, so these are not equal masses. However, this has its mass much farther from an axis of rotation. This one has its mass closer to the axis of rotation. Plus, this stuff is very solid. It doesn't shake, or it doesn't slosh around in there. So one of these should get to the bottom well before the other one. And again, it's the one that has its mass more close to the bottom. And you saw that little one got made it to the bottom first. This guy is obviously a much bigger circle, and I don't have one to race it with here, but if they were both hollow, both the same, they'll get to the bottom at the same time. All right, and if you can tell, releasing them, those guys got to the bottom at the same time, okay? So please, what I want you to start visualizing are I's. I's is called the moment of inertia, the I, the distribution of mass, mr squareds. If the mass is far from an axis of rotation, it's difficult to rotate. If the mass is close to the axis of rotation, it's easy to rotate. Just ask any figure skater who tucks their mass closer together and goes nuts. Any gymnasticator, they know that. Certain positions they can flip around like crazy. But anyway, I'm coming up on 15. Yay! physics.